I want to spend some time talking with you today about using Riemann sums to compute a function, the integral of a function, the definite integral of a function, or the area between a curve and the x-axis. In particular, I wanted to focus on the case when the partition is not uniform. That is to say that that delta x varies. So I'm going to draw a picture on the board here. So let's take that to be my function, and let's consider what's happening between A and B. So the limit, so the integral is this area right here. So there's some negative, which is going to cancel out. So it's like pretty much this area right here. Looks like this is a little bigger than this one. Pretty much this area right here. We've been doing this by partitioning from A to B in a uniform sense. So consider that all of those points are equally spaced. If these if those are equally spaced, then we say that the partition is uniform. So the partition is uniform because it's the same, right? It's just like wearing clothing in a Catholic grade school. Like, it's uniform. Everybody's wearing the same thing. So they're equally spaced so that all of these are delta x wide. But it doesn't have to be the case that your partition is uniform, because your partition could very well look like this. So let me draw it another way. We could have only a little bit right there, and then we could have really dense spacing of our points there, and then more dense right there, and then say more dense right there. So in this case, I've still partitioned the interval from A to B. It's just that it's not equally spaced. So if it's not, then the partition is not uniform. So in this particular case, I don't just have one delta x. I've got a delta x that depends on which interval I'm talking about. So that's right. So I've got a bunch of different delta x values. Here's delta x2, delta x6. So in the definition that's written up here, this delta x right here doesn't have a subscript on it, so it's not allowed to vary with which interval x sub I star lives in. And that's it's annoying because it's not flexible. So the change that I want to make right now is I'm going to put a subscript on my delta x, so that it's the width of the interval that goes with the interval that this xi came from. So when that's the case, you can't just take delta x and pull it out front of the sum here to make your life easier, right? You can't just take your x sub I stars, put them in a table, take our f of x sub I stars. That's supposed to be a paren. So here's my nicer paren, right? So I can't just go x sub 1, x sub 2, x sub 3, x sub 4. I'm doing right endpoints if I do that. So I can't just do right endpoints and then go f of these things, f of x sub 1, f of x sub 2, f of x sub 4, or whatever it happens to be, right? And what I've done before is I've been all okay, well, I'm just going to take the sum of these things and then multiply by delta x. But that's not the width of all of them, so that'd be wrong. So in this particular case, when I don't have a uniform mesh, I really need to add another column, which is my area of rectangle sub I. So I wrote that as area sub I. It's probably not the prettiest notation ever. I don't care, right? And so I'm going to get the area of this first rectangle by taking f of x sub 1 times delta x sub 1. That's off camera a little bit. So height times width, right? f of x sub 2 delta x sub 2, f of x sub n delta x sub n. So when your mesh is not uniform, you have to do the areas of each individual's of each rectangle individually, which for doing by hand calculations sucks. A computer will readily comply with this, and is not willing to complain at all about this. One question that you might be asking yourself is like, why not just make the partition uniform? Like, why even play this game at all? The reason is that rectangles are what are typically used in computers. We actually tend to use trapezoids or some other method to do this. And the way that I'm going to break up this interval is I'm going to approximate it with, say, trapezoids. So I'm going to approximate it with trapezoids, and like I could do one big long trapezoid in here. There's no reason that I want them all to be all small like that, like, right? I could just be like, well, why not just have one trapezoid for this whole thing right here? Because this thing wasn't curving very much. And then whenever I have more curvature to my integrand, I'm going to add more. I'm going to add more rectangles. So we're going to have more. Or trapezoids. I'm going to have more trapezoids wherever the function is curvier, and I'm going to have fewer where it's not curvy. So not having a uniform partition is advantageous for computer numerical integration because you can have an adaptive mesh. You can have the smallest number of points and still get really good accuracy on your estimate for what the area is, but not have to use a ton of points. The downside is that the by hand calculations mean that you have to compute each area individually. For that non-uniform partition. So I think it's good to be aware of the fact that the partition is not always uniform and know how to deal with it by hand, and also be grateful for the simplification. Oh, it was a uniform partition. Delta x is equal to b minus a over n, which computationally speaking, computers don't do. But we like it. So thanks for watching, and I hope you have a lovely day.